Let's keep going. State the interval over which this function is continuous. Now, it's a rational function. So I said earlier that if you have a rational function, it is continuous over its entire domain. So really, you just need to focus on factoring the denominator, which is x times x plus 2. So I actually have two vertical asymptotes. I have one is x equals 0, and one is x equals negative 2. So it's going to be continuous on its entire domain, which is negative infinity to negative 2, negative 2 to 0, and then 0 to infinity. All right, so let me show you the graph of this, and you can see that we'll have those pieces where it is continuous over this entire domain of this function. So x minus 1 over x squared plus 2x over x squared minus 2x plus 2x plus 2x. Confirm. Yes. All right, so there it is. I'll put the asymptotes on there. I found x equals negative 2 and x equals 0. I'll make them dotted lines so you can see that they are, in fact, the asymptotes. Okay, so when you look at this, you'll see that we approaching this negative 2 value and this 0 value. We've got infinity going on, right? Positive infinity, negative infinity. So it's discontinuous at negative 2 and 0, but it's continuous on all other parts of the domain. All right, so it has infinite discontinuity at x equals negative 2 and at x equals 0, but otherwise it's continuous on all other pieces, all other intervals. Okay? All right. State the interval over which this function is continuous. So again, I'm going to go to Desmos and graph 4 minus x squared, the square root of all of that. Okay, so we have the square root of 4 minus x squared. Okay, and it looks like our domain is negative 2 to positive 2. Now, here's how you make sure that it's okay. As long as you approach this point that's on the far left, as long as you approach it from the left and it's defined, right, there it is at 0. And as long as you approach this point on the far right and you get a value, boom, that's also 0. It doesn't matter if they're the same. But as long as you approach them from the left and from the right, respectively, right, from the left, from the right, then it can be continuous over that entire interval. So this function, the square root of 4 minus x squared, is continuous over the entire domain, negative 2 to positive 2. So continuous over negative 2 to positive 2. All right, let's keep going. Almost there. Now, there's this composite function theorem that states that if f of x is continuous at L, and you have the limit as x approaches a of a g of x function, so a different function, is also equal to L, then if you were to look at the limit as x approaches a of the composition of those two functions, you can take the first function and move it in front of the limit, and it multiplies by whatever you get of that limit. So let me show you with this one, right? So the idea is this cosine function, right? This cosine function is that first function. So it's going to move to the front. So the cosine of the limit as x approaches pi over 2 of x minus pi over 2. So we're going to focus on the inside first. So to find the limit, I'm going to plug in pi over 2. When you plug in pi over 2, you get pi over 2 minus pi over 2, which is 0. All right, so we have the cosine of 0. And as long as we can define that, cosine of 0, which we've done before, right? This is the quadrantal. So we have 0 over here. The ordered pair is 1, 0. So the cosine of 0 is going to be 1. Okay. Now, this one I put the proof here to read about if you are interested in. You don't really need to know the proof, but I put it down here in case you wanted it as a reference point. But essentially what I need you to know is this theorem, which is that trigonometric functions are continuous over their entire domains. And this hopefully makes sense to you because last year when you learned about the graphs of these trigonometric functions, you would have seen the sine wave, the cosine wave, like all these different ones are continuous over their entire domains. The only one that might be a little bit tricky as if you remember about tangent. Tangent does have some asymptotes, but again, it just means over their entire domains. So even though your domains might not include everything, like all real numbers, they're still continuous over their entire domains. Okay, let's go to the last thing. This is probably one of those things that kind of like the squeeze theorem is a little bit complicated, so I'll have you read Calculus for Dummies. We'll practice it here. I'll try to do my best to explain it. And then ultimately, you're going to find out in a Desmos activity, hopefully, you'll be able to solidify your understanding a little bit more after that activity. So here's what the intermediate value theorem is saying. It says if you have a function and it is continuous over a closed interval from any points A to B, so you just pick your points. If Z is a real number between f of A and f of B, so again, I always tell my brain that Z is like your Y value, then there is some number C, this is an X value, that in that interval that satisfies f of C, the X value, equal to Z, the Y value. I think the illustration here is helpful. All right, so I'd focus on maybe the graphic to help you kind of understand it. Okay, so we're going to show that f of x equals x minus cosine of x has at least 1, 0. So to use the intermediate value theorem to do this, I need to find a y value with its corresponding x value that gives a y value that's below 0, right, less than 0, or a negative y value. And then if I can find a corresponding x value that gives a y value that's above 0, or a positive number, then if I find some x value in between those 2 points, I will know that it must have crossed the x-axis, right? To go from a negative y value to a positive y value means that we would have had to cross the x-axis at some point to get at least 1, 0. All right, so I'm going to plug in 0 first. All right, so I'm going to do f of 0, which is 0 minus the cosine of 0. Now, we've already talked about the cosine of 0, right? Cosine of 0, just said it earlier up here. Cosine of 0 is 1. So this is going to be 0 minus 1. So f of 0 is equal to negative 1. See how that is negative or less than 0, okay? So now if I find an x value that gives me a y value that is a positive y value, I'll know that there must be a 0 in between those two x values. So I'm just going to do the next part of the quadrantal, right? If I use 0, change colors here. If this is 0 in terms of our radians, then this next part of the quadrantal is pi over 2. So I'm going to plug in pi over 2 into this trig function. So we have f of pi over 2 equals pi over 2 minus the cosine of pi over 2. Okay? So pi over 2, I'm just going to leave like that. You can get a decimal if you wanted to. Minus the cosine of pi over 2. If we go back to our quadrantal, right, the ordered pair for this pi over 2 up here is 0, 1, right? That point is 0, 1. Cosine is always the value that's in the x-coordinate, so it's 0. So the cosine of pi over 2 is 0. So if you subtract that, you get pi over 2. Now, you may not know what pi over 2 is. You can write it as a decimal, the approximation, whatever you wanted. But the key thing I care about is that this is a positive number. So there must be at least 1 0 between 0 and pi over 2. So there is at least 1 0 between 0 and pi over 2. So that's using the intermediate value theorem to prove there's at least 1 0. Now we'll go to Desmos, and we can go ahead and graph this. I can show you where that 0 is for x minus cosine of x. X minus cosine of x. All right. Now I'm going to change, you don't have to do this, but if I change my step to be pi over 6, you can see what we graphed the pi over 2. So here's 0, negative 1, that first point I found. And then pi over 2 is right up here, right about there. Okay, so that's the positive y value of about 1.5. And then we have the negative value of negative 1. So there must be a 0 in between there, and the 0 is actually right here at 0.739. So you can confirm that we have a 0 there. Okay, let's keep going. If f of x is continuous over 0, 2, and f of 0 is positive and f of 2 is positive, can we use the intermediate value theorem to conclude that f of x has no zeros in the interval 0 to 2? So this is an interesting thing because when we just talked about the last problem, we were looking at one to be negative, one to be positive, we must have a 0. Now the thing here, guys, is that they're trying to get you to think, well, if they're both positive, there can't be a 0, but there could be. We can't actually use the intermediate value theorem to conclude that this function has no zeros in this interval. We can only use it to talk about finding a point that's in between it, okay? So let me show you an example on Desmos that would actually be true for this and still have a 0. So let me show you one of those. Let me get my step back to be 1. Okay, so if I use this function, this quadratic function, x minus 1 squared, you'll see that f of 0 is positive, right? Positive 1. F of 2 is positive, right? At 2 comma 1, right there. But there still is a 0. There is a 0 right here, 1, 0. So this is an example of a function that is true for both of those statements, right? They're both positive, but it does have a 0. So just because we say they're both positive doesn't mean we can rule out that there is no 0. Okay, so anyway, just something to think about there. I'll try to do more of that in class. The last one, when you apply when you look at this one, 1 over x, we have negative 1 is less than 0, and then we plug in positive 1, you get greater than 0. Can we conclude that there is a 0 in this interval? So be careful. One of the things about using the intermediate value theorem, if I go back to that slide, is that f is continuous over this interval, right? So if I go plot this this function 1 over x, right? If I use Desmos to plot it, 1 over x, zoom out a little bit. Remember, we're going from negative 1 to 1, so there's our points, negative 1, 1, positive 1, 1. But if you look at the interval, negative 1 to 1, it is not continuous. This one is approaching negative infinity. This one is approaching positive infinity. So it is discontinuous across that interval, right? It has infinite discontinuity at 0. So it is not continuous. So even though you think, oh, that sounds good, right? We should be able to find a 0. You must make sure that your function is continuous over the interval that you're looking at. So since it is discontinuous in that interval, you cannot use the intermediate value theorem to conclude this. So let's see, f of x has infinite discontinuity at x equals 0. So we cannot use the intermediate value theorem. Okay? So that's one thing kind of to check to make sure you decide that you want to try to use it. All right, so hopefully you guys will have better understanding of continuity after this. We're going to practice a lot, lots of activities on the computer. So we should be hopefully getting ready for our test soon enough. Good luck.